All right, so when we study electricity, it turns out that in order to get electric current to flow, you have to have a pretty specific arrangement of components. And in particular, you need to have what we call a circuit. So the word circuit is used more broadly in English to just mean loop. So it's used, for instance, to talk about racetracks and stuff that are circular. So the reason that we use this word for electricity is because we also need to form a loop with the electrical components. So in particular, we're going to have a battery, and then this is the symbol for a light bulb, and then a loop that goes back to the battery. Okay, so if you don't have a complete loop, then nothing will happen. Essentially, in order to have the light bulb light up, you're going to need to create this entire circuit. Okay, so one of the things that is often really useful is to think about the current in a circuit. All right, so we're going to imagine that we have a flow of something that goes through this wire that way and through this wire that way. Okay, and there are a lot of things that are not obvious about the current. Okay, so one thing that is a bit of a surprise is it is the same at all the different points in the circuit. So I have some current that is going towards the bulb and some current that's going away from the bulb, and those two amounts of current are exactly the same. It's not just that there's a small difference, there is no difference. Okay, so what we find from doing experiments where you test this is that the current is never used up. Okay, and there are a variety of ways that you can measure the current. Like there are specific devices for doing that called ammeters, but actually it turns out that if you just place a compass near the wire, the compass will be deflected a little bit. So for instance, here's my wire, and here is the direction of the compass needle beforehand, and then when I turn the current on, the needle will deflect and it'll point this way. Or if I reverse the direction of the current, it'll point the other way. Okay, so what the compass tells me is not which direction the current is, but I can tell that if I flip the current, then the behavior of the compass flips. Okay, so we can tell both the magnitude and whether the direction changes or not with a device as simple as just a magnetic compass. Okay, so if we were under normal circumstances, you'd get a chance to measure this in the lab, and you would discover that the current is the same before and after the light bulb. For now, you have to essentially take my word for it. Although in the lab this week, you'll get to play around with some simulations that will show the same thing. Okay, so you might wonder why I have the current going the way that it is. So remember that the battery symbol has the plus by the longer wire. So this actually dates back to the 1800s. So they knew that we had a positive and a negative charge associated with the battery. And that's why they labeled one side plus and one side minus. So in case you're wondering, the little nub on a battery is always on the plus side, and the flat side is the negative side. So they figured out that they needed to have a circuit where some stuff was going on over here, and then it comes back to the wire, or comes back to the battery, I mean. But what they didn't know is what was flowing. Okay, so they had a suspicion something flowed, but they didn't know what. So they could either choose to go from positive to negative or from negative to positive. And it turns out that there's no experiment that you can do with just circuits like this that will distinguish between them. Okay, so current could be going either way. There was no way to distinguish whether we had positive charges that were flowing from the positive end of the battery or whether we had negative charges that were flowing from the negative end of the battery. So people made what they considered the sensible choice, and the convention for this is that current is positive charges flowing from the positive end of the battery. All right. Now, of course, today we know that, in fact, electrons are flowing. And electrons are negatively charged, and they're flowing from the negative end of the battery. However, we are still stuck with this 200-year-old convention. And so the current is defined to go from the positive end of the battery through the circuit and into the negative end of the battery, even though what's actually flowing is the electrons, which are going the other way. So try not to be confused by that. I'm always going to just refer to current and pretend that we have positive charges flowing. We will see that there are very few cases where you can tell the difference. Okay, so that's just a convention, but let's look back at this idea that the current is never used up, because that's often really surprising for people. You might think, okay, but like clearly the current enters the light bulb and then some of it gets used up to make light and then there's less afterwards. But that is not correct, because you can actually do the measurement where you measure the current in both spots before and after the bulb, and it is the same. And if you think of that as being in terms of electrons, electrons are not being used up in the bulb. They're not being burnt and turned into something else. The electrons are electrons. They stay the same before and after. Okay, so the big takeaway from that is that current is not energy. Okay, if current were energy, then energy does get used up in the bulb. We know some of the electrical energy in the battery becomes light energy in the light bulb and then, travels out to the rest of the room. So energy is used up. Okay, but the current is not. Okay, so this definitively tells us that the current is an energy, which shouldn't really be surprising because we know that the current doesn't get used up. It's electrons that are flowing, and the energy does get used up. But it still tends to throw people that is the case. All right, so the most important rule about current, if you're only going to remember one thing, current is never used up no matter what the situation is. The fact that we have to build a circuit as a loop also gives us a little bit of a clue about how light bulbs work. Because if I draw a battery like this, and I attach a wire, and then a light bulb kind of looks like this. It's got a pointy end, and then there's sort of the screwy part like this, and then a bulb and a filament like this. So if I just go like this and have the nub of the light bulb touching a wire that goes back to the battery, it turns out nothing happens. The light bulb does not light up in this circumstance. And this, again, is an experiment you would ordinarily get to try, but for now you'll have to take my word for it. And after some trial and error, what you find is that what you need to do is something a little different than this. So this does not work. Right. Instead, the arrangement that will cause the bulb to light up looks like the following. So I'm going to have a wire that touches to the nub of the bulb. But then another wire is going to touch to the screwy part of the bulb like this. Okay, so two separate wires touching to two separate parts of the light bulb. And then the bulb will light up. Okay, so the reason that this happens, there are two special spots on the bulb, just like there are two special spots on the battery. Okay, one of the special spots is the nub, and the other is the screwy part. So let me zoom in on a battery, or rather a bulb, and show you what the inside of a bulb looks like. Okay, so if we have the screwy part like this, and the nub, there's actually some insulator in between. So there's like some black glass that is connecting those parts together. And then there's another insulator that makes up the glass casing for the bulb. And if you look closely at a light bulb, there is a small filament inside which is attached to two wires, kind of like this. And it's not easy to see where the wires go. But if you break open a light bulb, which if you do that, please be careful, what you'll see is that one of these wires connects down to the nub at the bottom, and the other goes down and then attaches right about here. And if you look closely at any incandescent light bulb, you can actually see the glob of solder at the top where that wire connects. Okay, so in this circuit that I drew up here, where we have light coming from the bulb, we have one connection that goes to the nub and another connection that goes to the screwy part. Okay, so we can actually follow the current through the bulb. So the current goes from here up through this wire, through the filament, down this wire, and out the screwy part this way. So what a light bulb does is it actually is just a really weird shaped wire. And the light is generated when the electrons are forced through this really narrow part here. That piece of wire heats up and becomes so hot that it glows, and that's the basic way that a light bulb operates. So you should think of a light bulb not as some sort of mystical piece of technology that just somehow makes light. It's actually pretty straightforward. By forcing a current through a really narrow wire, the wire gets hot and glows. The rest of the light bulb is just to make it so that it's safe and efficient and doesn't burn out immediately, but the general idea is pretty straightforward.